Hello everybody, my name is Marco Pritoni. I'm a Ph.D. candidate in mechanical and aerospace engineering here at UC Davis, and I've been with the Western Cooling Efficiency Center since 2011. I'm going to briefly talk about this topic today. I hope to be quick. There's a lot of data. I try to synthesize it, but it's sort of hard. So we're going to talk about context of these devices, which are occupancy-sensitive adaptive thermostats. We're going to talk about the technology and other studies, about our field study here in Davis, and conclusions and recommendations. I think you're probably familiar with programmable thermostats. Many studies in 2006 and 2007 showed that programmable thermostats don't necessarily save energy. In some cases also they use more energy than manual thermostats. For this reason, in 2008, Energy Star terminated the specification for programmable thermostat. So following that, from 2010 to 2014, Energy Star has been working on the specification of a new product called Climate Control, which is not a programmable thermostat, but is a connected programmable thermostat, is another name for the same thing, but has a capability of communicating in multiple interfaces. It's kind of curious that this whole process took 4 years. I was working at that time with Alan Meyer and other people, as you see from the paper down there, and we were showing that programmable thermostats do not have good usability, or in other terms, are impossible to program. So we showed this in the research, and Energy Star considered specifying technical details about usability and requiring that. However, the whole process didn't go very well, and in 2013 they decided to withdraw all the proposals, and they waited. One of the reasons of this is that in the last 5 years, new companies, products, and business models had emerged in this area. Actually, before that, nothing really happened for 4 years. And then at one point, Nest showed up, and Honeywell caught up with a bunch of new wireless thermostats, and then EcoFactor, Ecobee, all new devices came to the market, and they are now available. Additionally, some of the companies like Honeywell is partnering with Power to give a completely different angle to the thermostat problem in the residential sector, and trying to include also behavioral suggestions to the mix. So it's not a technology anymore, but it's a service provided. So smart thermostats are not easy to define. They are evolving very quickly, and they are mostly a software product as opposed to a hardware product that they were before. So while EPA is trying to catch up and define what the specification of the hardware should be, like for example a washing machine, she's also trying to change the perspective, because this is software that can evolve very quickly. Like, we could have a different release every month, and it's really hard to frame and control. I don't think EPA really wants to control this process, just wants to ensure that the algorithms and the products that are offered now generate energy savings. So anyhow, some of the features that the so-called smart thermostats offer are multiple interfaces, including web, mobile, and tablet interfaces, improved feedback through these interfaces, occupancy sensor that triggers set point adjustments through sensors, light sensors, and even GPS. They might include learning capabilities that we call adaptive capabilities, in a way that they learn the thermal response of the house or the occupancy patterns, and this is, for example, Nest, and they try to predict temperature preferences. Optimization is another important feature that has been developed. In particular, I want to mention EcoFactor, that has been trying to produce automated savings without user effort and user engagement, but just learning what the user wants and try to get savings whenever they can. Also, capability of communicating through demand response with the grid is another feature. As I said, O-Power is trying to come up with ways of influencing behavior, and fault detection and diagnostics is another important feature. So if you browse the web, there's a lot of products and a lot of claims. Some of the thermostats claim savings from 10 to 30%, which is pretty common. Some claim savings of 70% in some cases, and sometimes it gets kind of ridiculous. So this is, I don't know if you saw this, this is the newest of the new, which is the new Honeywell on the left, which is sort of inspired to the Nest, which is inspired to the old Honeywell round. So it's kind of they're adaptive techniques that we also call learning are really promising in this sector. Indeed, programmable thermostats were never programmed in an appropriate way. And as I said, they have low usability, so people wouldn't change them. If they have an updating schedule, people would not just either push them a hold button and keep them there, or they don't deal with it. Most of the programmable thermostats were in practice turned back into manual thermostats. To be honest, I have that tendency too. Here in California, the climate is pretty mild, and my control of the thermostat is basically complete. It's always off unless my wife complains, and then it's on. So I don't need a smart algorithm to do that. But in other climates like Midwest or where cooling is also required most of the day, or it's really humid, this device might save a lot of energy. Going on, this is the technology we evaluated. It's called Telconet. It has an occupancy sensor, or actually multiple occupancy sensors, and it's attached to a mesh network of other devices like this. The characteristics are these. Very briefly, there's an occupancy sensor and a light sensor that combined give an idea of the real occupancy of the room. Indeed, some of the pure occupancy sensors don't work really well during the night, so they might not perceive if people are sleeping or not. So that's kind of adjusted by that. They have a Zigbee wireless network they connect to. They learn basically the thermal response of the building. So what they do is they detect when people leave the room, and then they turn the temperature down or up, so they set back based on a specific number that the facility manager in this case can put. For example, if I want to be back to the temperature I set in 15 minutes, I just set that 15 minutes into the device, and the device automatically calculates how much time it takes, and it never lowers the temperature below that new setback. So the setback is not manually input by the user, but it's automatically calculated. This is kind of an original approach, and has been interesting observing in the field how this impact the energy use. Another important thing is that a facility manager can set a band of maximum and minimum temperatures that the user can set. So you will not see any more dormitories at 62 in the summer or 95 in the winter, but they are limited to a band, which is also can be fixed. So this is just to show you how this behaves. In gray the room is occupied, and white is unoccupied. So in the first graph up there, the room is mostly occupied, and the temperature, this is heating. The 70 is the temperature set point, and the temperature oscillates around that value. In the few little intervals in which the room is unoccupied, you see the temperature drops more than on average. In the graph below, you could see that the room is unoccupied for a couple of days, and the temperature decreases significantly. You can also see that there's missing data over there that we'll discuss about later. So the impact of this on runtime is the following. As you can see, this is the runtime of the first case, and this is the runtime of the second case. It's really clear that the system is running less. We were interested before even going there to see what the literature claims were and where other experiments were conducted. So there were, I'm not claiming these are all the studies over there, there might be more, but there were not many studies on this kind of technology. The first one is a simulation study that is not a field study, and it covers different technologies and says the savings should be around 10–20%. The second and third one are field studies, but they are in guest rooms. So this is we're trying this technology in dormitories that are very different. The buildings are more massive. The occupancy has different patterns and stuff. Plus, the methodology used by these two studies is not really rigorous. So,
you mean by guest room? You mean a hotel room?
Or hotel rooms. Okay. Yes, those are hotel rooms. So, the methodology-wise, one of these studies compares rooms turned on and off so one room is on and the next room next to it is off, etc. And they try to calculate energy savings by runtime. In the other study, I don't remember which one is which. In the other study is mostly about small systems inside the rooms, so not built up HVAC systems. There's a bunch of, at the end, Telconet studies that also use runtime as opposed to energy measurements as a proxy of energy savings. And you can see savings are significant in the order of 40%. Again, these are hotels and motels. So we were very interested in knowing, because we have a partnership with CIEE, what was the possible application of this technology in university dormitories. And as you can see, this is a paper that my colleague Jonathan wrote a couple of years ago, and he shows the potential of these technologies from more appropriate to less appropriate, using as a metric the occupied hours. So if the building is occupied, the occupancy is very low, so this technology is probably will do well. And if the schedule is not very predictable, you can't really put a schedule in the thermostat. So that means that the thermostat would perform better than either a manual use or a set schedule. So the best cases are on the right up, and you can see hotel rooms over there and conference rooms. So instead, resting results are on the high left, and so they're not complete, they're not perfect, but they have potential, and we'll see the impact of this. So we're not just evaluating the technology, but technology plus the context, which is a university application. We studied this in 4 buildings. Those are a complex of 4 buildings. Each one has 110 rooms. There are 40,000 square feet each, and they were originally built in 1965, but they got renovated in 2011. One of the features they got introduced are these thermostats. So this is the plan of one of the floors. As you can see, the rooms are on the north side, on the south side, while the area in yellow is a common area that includes restrooms, laundry rooms, and other common rooms. The common rooms are not controlled by the thermostat. which means that the system we are analyzing controls more or less around 50% of the space in the building. This has an impact, and I'll show you why. Most of the rooms have 2 occupants, and a few rooms, I think 2 or 4 per floor, have 1 occupant. Interestingly, this has another effect on the energy use, because the occupancy of the room is the combination. So the room to become unoccupied has to measure no people inside. So both of the people have to leave the room, which means unless they have similar schedule, they're going to conflict with each other. They're going to have a conflict with each other. The HVAC system in this building is a fairly complex built-up system. It takes chilled water and hot water from the campus loop that gets into the building. It's a 2-pipe system, and each room is served by a separate fan coil, and the fan is a 3-speed fan. So it's a fairly complex system and flexible. Each thermostat controls the fan coil. We had a lot of data, so this is for sure. I got interested in this project mostly because there was a lot of data, and I said, well, where there's data, there's things to understand. And then we realized that there were millions of points of data, so Excel would just blow up and other things happen. And so this was a good test for us also to test new tools. So we tried Python, we tried MATLAB, we tried Simulink, we tried R, and we tried other things that now have become part of our process of analyzing data. We have 2 main data sources. One is the Siemens EMS that controls the chilled water going into the building and measures the energy at building level. We don't have a measure of each room in terms of energy use, but we have measurements from the Teleconnect thermostat that measures when it's calling for heating, cooling, occupancy, fan speed, and light level. This colorful graph shows that we have multiple baseline with periods that are pre, post, etc., and I'll explain you the details in a following slide. Reading the literature, we realized that many of the studies we had about technologies like this were not well documented as a minimum, but we thought the design process of the experiments was not particularly careful. So I don't know if you are familiar with ASHRAE Guideline 14, but it gives a standardized method for measuring energy and demand savings, and it's been written also to be a common baseline for different stakeholders. So if there's an third-party energy contract company that gets paid by savings, then this guideline defines what the agreement should be. It basically answers the question, what is pre, what is post, and how much savings am I getting? And it also defines what are the metrics, what variables you should include, what you should measure, and uncertainty. This is a guideline, so you can choose between different paths. Actually, there are 4 paths. 3 that we were thinking of using are the whole building monitoring, retrofit isolation, which is you get only one RTU when you measure that one, or the whole building calibrated simulation. We didn't want to go to calibrated simulation because it's a painful and long process, and we didn't have resources on this project. But we considered both the first one and the second one. One important problem we had is that this guideline requires 12 months of pre and post data, or at least a wide spectrum of all possible weather conditions and occupancy conditions. And this was a problem because the building got retrofitted right before the installation of the thermostats. So we didn't have a reliable pre data. And at the same time, the devices that were giving us this new incredible data set with the temperature and occupancy were only recording data after the installation. So we didn't have, for most of these buildings, a reliable pre-period. The guideline also defines how you should, what you should use as a baseline, and I'll show you what we developed. So we really wanted to use this. However, as I said, we had fragmented data, missing intervals, sensor not working properly. At the beginning, there was an initial period in which a connection was lost. Things got better, but still we lost several days of data for each device. And you have to think there's 110 rooms times 4 buildings, and each room is providing data that could be missing some pieces. So when you have to combine them all together, it's really crazy. So you have to define metrics, and we did that, but it was not an easy process. Another interesting piece is that Telconet is optimizing data recording based on their needs of communication. So instead of recording how engineers would like 15 minutes intervals, they record every time they can send a packet to the network. So you have one interval is 15 minutes, one is 10, one is 25, one is 5 hours. And so you had to interpolate, and that's fine. I mean, temperatures can get interpolated really easily, but some of these data were runtime, which are integrals of things. So X% of this time, the system was on. And when you had to reinterpolate that data, it becomes pretty messy. And with missing data combined with this, it was really complicated to sort it out. What we did, we got the baseline for some of the buildings, but still the rooms were not instrumented one by one. We didn't have a measurement of the chilled water coming into the fan coil and going out. So this, plus the fact that the building was controlled with the new device only, the new device was controlling only about 50% of the floor area, gave us a bunch of things to think about during the calculations. So what we did is we used a hybrid whole building and retrofit isolation method. We used pre and post energy analysis where it was possible. And when we switched to a week on, week off energy measurement for 2 buildings that you see in the picture, they are Michael and Gilmore, and they are basically very similar buildings. I wouldn't say almost identical, but they are very similar. The systems are similar. The position the orientation is similar. Overall, the occupancy was following the same patterns. So what we did was we switched on and off the features that allow occupancy to be part of the set point, to influence the set point on one and not the other for a week, and then we switched. The other week was the first building, then had the features enabled, and the other one had not. Another important thing is to capture at the best of our possibilities the fact that both weather and occupancy of the buildings are very variable for this building. We kind of divided the year in different periods. So you see operation is cooling and heating, and these buildings only do cooling or heating for each season. They have to be manually switched to another system, so they don't cool and heat in the same day. So there's only either chilled water or hot water going into the pipes. Okay, so those were different periods, and occupancy was high and low. We did get cooling data, but we had several problems with heating data. So heating data is not included in this presentation. Some of the sensors at building level were not working properly. They got recently installed, but then we didn't have time to analyze data. So what we did is applying guideline 14. So we got the pre-period in case of pre-post, and we created a baseline. This baseline gave us, through that ugly regression model, a way of calculating those parameters, which are beta 0, beta 1, beta blah, 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 blah. And I'm not going into details, but if you are interested, I can give you the paper we wrote about this. And then we are using the values of temperatures and occupancy of the post period to create a projected baseline and compare the projected baseline with the real data of post. So the energy savings are calculated, again, as a difference between the post data, real data, and the projected baseline of the pre-data. Same things for week on and week off. Basically, when the week was off, is calculated as a pre-intervention, and when the week is on, so the feature, the occupancy responsive features are activated, then that's basically the post period. Same thing, same formulas. Results. So this is only cooling data. Basically, the results are these. Both from pre and post and from on and off, when we measure data in the spring, in the fall, at our academic periods during cooling, the savings were very, very low. And this means not around 0 to 5%. Most of the cases were not statistically significant, so almost zero savings. While during the non-academic year, the savings were much bigger, around 20–30%. So we're sort of surprised at the beginning about this result, but then we kind of dig deeper and try to understand what's happening. So this is an example of the pre-post, and you can see on the left is a scatter plot of chilled water energy use versus outdoor temperature. In blue, pre, and in the opposite, in red, pre, and in blue, post data. They almost overlap, meaning the response of the buildings to temperature difference during the spring in Gilmore is almost the same. And you can see on the left the data overlap of the projected baseline and the measured retrofit. Some of the points are higher in blue, and some are lower. Overall, the effect is 0. Then we did on and off, and this is very interesting. So you can see on the upper graph occupancy during the spring, summer, and fall. And you can see occupancy vary every day. There's an oscillation every day. This is average building occupancy. So we're averaging all the rooms together. And it is around 50–60%. So the building is half occupied at the time. And there's a low moment there, which is probably spring break or some other thing. And this is pretty similar to what happens in the fall. So the occupancy is still very high, has a weekly pattern, a daily pattern. And while in the summer, the occupancy is almost 0. So another characteristic is that in the average occupancy of the buildings doesn't really describe what's going on in each specific room. So each room could be occupied for a few hours, and then people come back, and then they leave, and then they come back, and overall, the occupancy is 50–60%. But each room is unoccupied only for a few hours. While during the summer, the students leave, and the building is used as conference center. And so occupancy is mostly 0 unless these rooms are occupied, and are occupied for a few hours per day. So the periods in which the room are unoccupied are not just overall more, but they last longer. During these periods, the temperature inside the rooms can actually drift to the setback temperature, and because most of the load is driven by, the hypothesis is that a big fraction of the load is driven by temperature difference with the outside. Reducing the temperature difference with the outside through setback reduces the need for cooling and then the energy use. So you can see on the bottom that in the spring and in the fall, the two graphs overlap the scatter plot, while in the summer, in blue, the measured performance when it's on is lower. So as it gets hotter, the energy use, which is on the y-axis, is lower in the blue case, which is when the device is actually set back in the temperature as expected. So this is Marco again, on and off during academic year, almost no savings, and then during the summer, as you can see, the projected baseline is much higher, which means it's using more energy. So we have energy savings here in the order of 20, 30%. So an interesting, we actually did a very deep analysis of room-by-room cases, trying to see if temperature inside the room, temperature set points, and runtime were a good predictor or not of the energy use, and the quick answer is no. In a building like this is kind of interesting. I just came back from a workshop organized by EPRI in Palo Alto, in which about smart thermostats, and some of the utility folks were saying that in residential, what they do to evaluate the program are, number one, they don't do pre and post, but they compare one household with another household randomly picked. And, you know, when you have 2,000 households, it's fine. And I was kind of shocked. This is a purely statistical approach. You clearly can't do this in a complex building as this one, because it's unlikely that any other random building you get is even close to this one. So they call this randomized control trial. And they do even another thing, which is even more interesting, which is called propensity score matching. So they get a household in which they do their treatment, in which case, in this case, they add this technology, and they get another household from the pool of all the households close by that looks similar. They cherry-picked it, and so it was kind of okay. And so they were complaining that pre and post was a biased method, and I was kind of shocked that their method is even more biased, but anyhow, the point here is that they use they try to use set points and runtime as proxy for energy, because it's cheaper to get them, because new thermostat manufacturers get those data directly, so they won't have utilities to do MMV. And it might be okay for residential. I haven't seen the data, so I can't judge, but for buildings as complex as this, it's not. This is an important thing we notice, and if you plot energy use in the building and runtime, it doesn't correlate. It correlates at 60% or something. It's vaguely correlated, but not entirely. And one of the reasons is you're not measuring in a system like this the temperature of the inlet and outlet of the loop. There's a 3-speed fan, so runtime, if you measure the runtime only on, then you have to give a weight to the fan speed, because it's removing less remote heat depending on the speed. And also because in a building like this, only 50% of the floor is actually controlled, and the other 50% is controlled in a traditional way, which is in most of the cases a fixed set point. So this was an important point that we took us a while to figure out, and we have detailed, again, they're not here, but detailed analysis of all the possible cases in which just measuring the runtime is not an accurate predictor, including when the system is running flat and the temperature goes up, or when there is thermal bleeding between rooms. For example, if you condition one room and you don't condition the two that are close by, they're in thermal contact with it, in a building like this, there's a lot of leakage, both air leakage, and the walls are so thin that basically your room is cooling the other two. And so when you measure this at room level, with varying occupancy between rooms, it gets kind of tricky to actually get the effect and not the effect on the environment that is around the room. So again, in cooling, higher set point don't always correlate to lower energy use for the same reason. And while we're doing this, we also realized that some of the cooling, reduced cooling energy use in a room that is not occupied is not due to the setback, but is due to the fact that if nobody's there, nobody's generating heat in there. And for a very small room, which it is, with 2 people, the internal load might be significant. So again, we realized that the academic period was very different from the non-academic period, and one of the reasons is during the academic period, the occupancy is high, but also vacancy is spread around the building. And since there's thermal connections between the different zones, you can't really set back and have an effect because it's going to affect everything that is around you, especially if the corridor is conditioned at 72, stable forever. So if you have a window open or a door open or other things, you're going to have the corridor working toward cooling your room. Again, we said this before, the vacancy is only lasts for a few hours, and the temperature can drift back to the setback point, and so you're not saving much energy. Other important points that we realize are that a system like this could give you additional benefits, and these benefits could be even superior to just the energy benefits. One of this, which is the last one, is that the operation management loved these devices, regardless of energy savings. And they installed 3,000 units in 25 buildings, and they did not wait us to tell them if they were saving energy, which is curious. And they did it because with one click, you can set all the thermostat to a setback, you can switch them off, you can have a feedback of what is broken, where is broken, you have full detection, automatic full detection. And think about moving a staff of 20 people to switch off all the devices, the last day of school. It's just crazy. And you can do this with just a click. Another important thing is if you did have, as in few of these buildings, an unconstrained thermostat before that nobody checked because nobody was going room by room to check, you could have, in paradox, a person having 62 during the summer and 84 during the winter and just leaving forever. And now you can basically click a button and put everything in setback all together, and also you can limit while they're there what's the set point band they can reach. And I understand there's a privacy or control issue here, but these are also students, so I guess they're flexible and they can go to the study room. We wrote a few papers on this project because it was very interesting to see how you could use data to get answers, even if the answers are not super clear, and how you can model these things with regression analysis and stuff. In the last paper, we tried to summarize things that could be useful for other application installations. And one is that we think we don't have heating data yet, but for cooling, we know that this technology have the potential to save a lot of energy during non-academic periods and in academic periods if the previous thermostats were unconstrained and people were just behaving not in a very environmental friendly way. This technology could be instead used in single-family homes, small and medium-sized commercial buildings, laboratories, and hotels, probably in a better way for different reasons. And I'm not going through them, but for example, laboratories have a huge ventilation load, and you can, if you have occupancy data, you can control that through that sensor. In office buildings, for example, it could be occupied in different ways. People could leave and not come back, and having fixed set point, even in the zone system, could be not a good strategy. Same in single-family houses, occupancy responsive thermostat like the Nest could be effective. Hotels have been already proven to be a good candidate for this technology. The difference between hotels and the residence halls we did experiments on are for sure that our building was more massive, there were more thermal interaction between rooms, the system was much more complex as opposed to a single unit just sticking out of the window. So recommendations for install. Clearly, mild climates will achieve smaller savings in magnitude. We recommend covering most of the area you have in your building in this condition with this technology. If you leave areas off, the risk of having interaction with the system and possibly not nullify the saving you could get. We also suggest to check if the operation of this penalizes the efficiency of the system. Clearly, this technology saves more energy in inefficient buildings in which there's a lot of thermal losses. As I was saying, Jonathan, the best use of this is an air conditioner with no walls. So if it's blowing in front of you and you have an occupancy sensor and you're not there, you're going to save energy.
I'm glad you shared that and kept the insight.
As you get to more sophisticated and buildings with higher thermal resistance and higher mass, then setbacking might not be that effective. But it depends. The answer is always it depends. Also, building with large ventilation loads could be a good candidate. We suggest a test, which is try to set before buying for 30,000 100 thermostats. Try to set back, unless you have operation goals. Try to set back one room in the floor, and just that one, and see the temperature drifts and how fast. If it doesn't drift, it might mean that you have connection with the other rooms and somebody else is cooling the room. So in that case, this technology might not be super effective. Also, if you know that your building has long periods of vacancy and or the average occupancy is pretty low, this could be a good technology for you. It was interesting also observing, I can go on forever, but some of the analysis we did is that in California, especially during cooling, you get savings if you are in the right direction, which I try to explain myself. It means that in California, there's a huge temperature swing during the day. So during the night, temperature outside is not as cooler than the temperature inside. So you're basically losing heat. So if you set back during the night when it's cold outside, you're not actually saving anything unless you have the walls and internal gains and etc. But the setback has to be coincident with weather conditions, with the driver of energy losses. So that's most of it. I'm closing with words of a wise man. This is an interesting add to the presentation, because the previous, before doing this, well, actually, somebody else here did another experiment in another building, and something went kind of wrong, and the system was doing nothing. So the installation, everybody thought that the building was configured in one way, but the control sequence was actually different from what everybody thought, including the people who actually managed the building. And so this thermostats got installed in another location, and they basically did nothing. And so the wise man says, seemingly minor details within complex system designs can have major impacts on actually operating characteristics. Small oversights in a system application might eliminate the anticipated energy savings benefits from efficiency measures. So this is a mechanical engineering point that sometimes statisticians and economists or other people with a different background kind of that they don't consider, but you need to be very careful, especially in complex buildings, that an add-on technology to the existing system has to be compatible with the existing system. Otherwise, it might have no effect, or even worse. That's it. Many people work on this. These are a few, the one I remember, and thanks, everybody.
Thank you, Marco. I now would like to open it up to any questions that you may have for our presenter. Give it a few minutes as you work your thoughts out.
Marco, I wonder, when you're looking at the breadth of different smart thermostat technologies, and I think that you have more experience here on our staff than anyone else related to smart thermostats. You started by outlining the variety of different things that they can do, and in this study, in these papers, we were very, very careful to isolate this sort of adaptive setback scheme. And so we didn't measure anything related to whether or not we improved energy use by constraining the set points so that people didn't leave them at wild points. But looking at a higher level at the entire breadth of smart thermostat technologies, what are the characteristics that you see that might be most effective?
We had an interesting discussion yesterday at this workshop organized by APRI with a lot of these manufacturers, and everybody was claiming, you're going to save, you're going to save, you're going to save. I think it really depends on the application. So this technology we evaluated is good for that specific application, and it might not produce anything in other cases. For residential, I think a new approach that might be promising is a technology. So there's two basically high-level approaches that are interesting, at least from my perspective. One is the complete automation of savings, which is what EcoFactor is doing, is I'm going to understand and learn when you're in the house, what's your temperature preference, what's the thermal response of your house and your system, and then I'm going to try to drop it and see if you react. And they have a thermal model, they have an energy model, so they try to manipulate your system so it produces no difference to you, but it saves energy. And this is like an optimization approach, and in a house that is not a super complex system could be interesting and produce savings. The other approach also for houses, which I found interesting, is Honeywell plus O-Power. So they are using Honeywell system just to get in the house, and then they use a bunch of behavioral techniques to suggest alternative options to the user. So they have, for example, the sliding temperature set point level that if you get to you're cooling and you get to a set point that's just too low, it changes from a smiley faces to a very angry face or sad face. So these things, I was like, this seems funny, but apparently it might have an effect. I'm gonna stop until it gets red. I'm okay with yellow, but red no.
Yeah.
So what they call coaching. So they provide you. They have layered level of information. So you have different interfaces, and I get you a report and this and that. And I try to tell you and give you suggestions when you are in the mood for change. So in this case, this is the opposite. It's the vehicle of energy savings become the user, as opposed to the system optimizing itself. So I found these two competing technologies and approaches very interesting, and they go beyond the just reacting to an occupancy or that I've seen in other cases.
What do you think about how, not to talk specifically about the Honeywell system, but they have an interesting occupancy sensing feature, whereas instead of using IR and all that jazz to see if someone's actually in the building or in the room, they actually have a smartphone app where it talks to the thermostat and it knows exactly how far away you are from your house. So then it realizes, oh, you're at work. It can tell based on your distance, knowing that it's kind of learned that, it knows now to set it back really far. And then it'll realize as you're approaching, as you're approaching the building or your home, that, oh, they're coming, then let's bring it back up again. Do you think that type of feature is more valuable or more reliable, do you think, than a standard, the way we do occupancy sensing today with IR and...
Yeah, so occupancy is a critical point, and many people wrote hundreds of papers on how you get reliable information on occupancy, given that the sensors might not work and you might have multiple people in the house and you might have a dog doesn't want you
doesn't have a smartphone either.
Doesn't have a smartphone and doesn't want to be freezed.
Not yet.
So this is, and I think this adds to the existing technologies. I've actually seen a research paper in 2009 about a guy from MIT who developed for the first time the GPS version of this. I don't know if they bought the same technology or if it's an alternative to it. I think it goes into the basket of I have something that tells me that I'm here or not. In terms of energy savings, again, it really depends on the system. It might not be particularly useful. I don't know. And in Chicago, where you can't drop temperature that much, otherwise it should really freeze. It might be different than in Berkeley when you don't really need conditioning at all.
Anyone have any other questions? No? Okay, well, I'd like to thank everyone here that have come to the webinar, and I'd like to thank Marco as well. Thank you for presenting today. It was very informative. I will be posting this online in about a month, but if you'd like it earlier, please go ahead and let me know and contact me directly, and I will send you the link. So thanks everyone again, and have a good day.